to Let's Talk Chemistry with Pastor Dan. We're starting a new concept today. We're looking at the periodic table. Now, the definition of a periodic table is organized representation of all elements by increasing atomic number. And I use the number Z. There's some confusion or discrepancy whether or not we need to explain that anymore. It's an old system. We don't usually talk about it too much, but I'm an old teacher, so I'm going to make sure it's there. Atomic number is all we're looking at, and the way they used to define it was a process of Z. All right, so who first came up with this? It was this guy. His name was Dr. Dmitry Mendeleev. Mendeleev was a Russian. Yeah, wunderbar. Now, he first organized the periodic chart, and it's called the father of the periodic chart. He organized it by light character, which was good, and atomic mass. That's all we had at the time. We identified the atomic masses from things, and from there, he's able to identify it. Now, if you look at the periodic chart over here, we start with, where are we at? Sulfur. Sulfur's 32. Chlorine, 35. Argon, 40. Potassium, 39. Calcium, 40. Now, that doesn't seem right because we're going back and forth. And with Dimitri's chart, you would have literally sulfur, chlorine, potassium, and then a big gap, argon, and then calcium. So there were all kinds of holes everywhere. That was a problem for his chart. Now, Dimitri's explanation, no problem. Obvious elements yet to be discovered. Now, was he right? Yes, many elements hadn't been discovered yet. Silicon had not been discovered yet. Mobilium, all those elements. So there were elements that had yet to be discovered, but there had to be a different way, a better way. So it took until World War I, around World War 1910s, 1920s, that a second scientist, his name was Dr. Henry Moseley, hip hip cheery old boy. He's a great Britain English. He worked at Oxford University, and he used a value called Z, atomic number. He found that using a cathode ray tube in calculus, high math. Now, you'll notice the life and death here of Dr. Moseley. He was very young. What happened is 1915, that's World War I. And because he was English and because England's at war, Moseley was sent off to the front line, and he was shot and he was killed. Because of that, the British Society, the Society of Science, petitioned Parliament, and a law was passed that if you are a scientist, you can't be sent to war. So if you're English and you're a scientist, if England goes to war, suggestion, become a scientist. All right, so here's what he did. He identified that, fixed the chart, put everything the right way. So we have specific classes, ways of distinguishing what elements are. Now, there are 3 different classes: metals, nonmetals, and semi-metals, also referred to as metalloids, but because M and metalloids can confuse, I just call them semi-metals. All right, what's the definition of a metal? A metal has 3 characteristics: has luster, malleable, ductile. Now, luster means that it shines. It gives off its bright in color. Malleable means that you can hammer it into shape. If you bang on it, it will bend. Ductile, it can be heated up and drawn into a wire. And conductive, it carries electricity. Now, you look at it, something like sodium. Sodium doesn't have a great luster. The reason for that is it's so reactive that the second it's exposed to air, it reacts and loses that luster. But it still has it for half a second maybe. So as a result, we still consider that a characteristic of a metal. Second characteristic of a nonmetal. Well, they're going to be opposite of metals. So nonmetals are dull. They don't shine. They're brittle. If you hate them, they'll break in many places. And they're insulated. They don't carry electricity current, or they don't carry it very well at all. Now, what are semi-metals or metalloids? Well, these are the ones with characteristics of both. They have properties of both metals and nonmetals. So aluminum. Aluminum is a semi-metal. Okay? It is shiny. It is malleable. It is ductile, but it doesn't carry electricity very well. And as a result, we consider that semi-metal. Now, we're going to use the periodic chart to find them. Okay? So here's the way that we're going to do this. Now, you'll find some discrepancy with people the way they teach it. The way that I teach it is we put a little line here between boron, aluminum, carbon, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. Now, some people put the other side as well. I just use the right side. If it's on the right side of that, we call those all nonmetals. So all of those on that side of the chart are qualified as nonmetals. The ones that are on the left side are considered metals. Now, where are the semi-metals? Where are the metalloids? Well, if it touches the line on the left side, and that's the way that I teach it, some people will include on the right side as well, but so that's the way I do it. Those are where the semi-metals. So if I was asked for manganese, that's a metal. Oxygen, non-metal. Bismuth, semi-metal. Hopefully that makes sense. All right, awesome. Next thing we'll look at is something called valence electron numbers. Valence electron numbers are the number of electrons in the outer shell. Remember we talked about the octet rule, the maximum number on the outside, so we know how many are there. So the way that we use that, again, periodic chart, real simple. We're just going to count the columns. First column, everyone in that column has one valence electron. Second column, everyone in that one has two valence electrons. Now, because of that D and F thing we talked about, electron configuration, we're going to consider all the ones because, remember, we're dropping down. All of those are 2, and then we're going to keep calling them. Boron down is 3, carbon down is 4, nitrogen down is 5, oxygen down is 6, fluorine down is 7, and from neon down is 8, but helium is still just 2 because we slid over, remember, with the electron configuration. And then the bottom 2, the F orbitals, because again, they're dropping down. We're going to say 2 valence electrons. So let's do a couple here. Let's say I give silicon. How many valence electrons does silicon have? Look up. It's right there. 4. All right. How about fluorine? Fluorine, right there, it's 7. Hopefully that's pretty good. Next, we'll look at something called ionization number and electron affinity. Now, these are actual numbered values. Ionization and ionization numbers and energy needed to lose 1 electron. So how much energy does it take to kill off an electron? Electron affinity is energy needed to gain 1 electron. So they're opposite processes. All right, so in reality, this is a number. Everyone has its own number, and it's expressed in kilojoules per mole. So we're going to talk about later. It's a unit of chemical reactions. All right, so how are we going to make this easy to understand? Let's go back to the periodic chart. Okay, so again, this is the way that I teach it so you understand the process. We're going to say how many is it easy to lose. So for ionization, losing, I can do everything in the first column is a first. I can lose 1 easily. How about the second column? Well, I can lose 2, so I can lose a first and a second. Aluminum here, it's the only one that we're going to say is a first, second, and third. It loses those 3 easily. All the nonmetals, including the noble gases, are 0. They don't want to lose any, they want to gain. They want to gain with a passion. And that means all the rest of them, all the ones that are not the first column, the second column, nonmetals or aluminum, we don't know. Actually, we do know, but they vary. Depends on what they're interacting with, and that includes the F range there on the bottom of the chart down here. All right, so for electron affinity then, again, this is energy actually, but we have to have a way of doing it. So let's just say it's either, does it want to gain, or does it not want to gain? Well, all nonmetals, well, most nonmetals want to gain. In fact, fluorine wants to gain with a passion. All right, that means every nonmetal and semi-metal are going to be no. How about these noble gases right here? Well, these noble gases are also no because they're filled shell. They don't want to gain anything at all. So all metals and semi-metals are no. Noble gases are no. Nonmetals are yes. All right. So last thing we'll talk about here before we, no, maybe not, we'll see, is electronegativity. It's a scale measure from 0 to 4, the pull of an atom on its electrons. Now, there's a chart in my book that I look at in order to identify it. We have 4 different bonds. Which one is pulling on an atom stronger? So we come over here. We look at the chart right here, and we see these numbers. And you'll notice I said fluorine really wants, fluorine is the only 4.0. It is pulling with so much force, it wants to go bad. So we come over here, sulfur and fluorine. Sulfur is 4. Sulfur down here is, where is sulfur? Right there, 2.5. Obviously, 4 is bigger than 2.5. So, sorry, I did the wrong one there. I did down here, fluorine and bromine. All right, sulfur. Let's go back again, wrong way. Sulfur is 2.5. Nitrogen is 3.0. So therefore, of the 2 of those, nitrogen will be pulling stronger. fluorine and bromine. Obviously, fluorine would be stronger. All right, oxygen and carbon. Oxygen's 3.5, carbon is 2.5. Oxygen's pulling stronger. And the last one is chlorine and chlorine. Well, they're both pulling with a pull of 3.0, so we would say they're the same, neither, equal. The bond is fine. All right, so last thing now that we'll look at is something called diatomic elements. Because of that electronegativity, these are so they cannot exist as a single atom. Or we have carbon that can be a single carbon atom, or sodium as a single sodium atom. There are 7 elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, that when they exist as an element by itself, only as an element by itself, they'll bond up with themselves, but they can't exist by themselves. We call this the magic 7. So let's go and look at the periodic chart again. Okay, and here are the 6 of the 7, and you'll notice that makes a nice little 7, so we call that the magic 7. So if you look at the chart and I ask you, is it diatomic? If it's in here or it's hydrogen, those are the diatomics. Alrighty, so tomorrow we're going to talk about families and energy levels. We'll discuss that later. So let's go to a practice. Here we go. So again, we're going to talk about families later, so we can leave this column blank and come back again. We're going to look at class. So that's metal, non-metal, semi-metal. Valence electron, that's 1, 2, 3, 4, 5, 6, 7, or 8. That's not a trait. Ionization energy, that's either first and second, and third. 0 or D and K. Electron affinity is going to be yes or no. And diatomic, again, is going to be yes or no. Is it diatomic? Is it not diatomic? Try these here. Pause the video. And then when you're done, we're going to go back and look at the answers. Okay? Alrighty, here we go. So for these, that's the answers there. Check through. Hopefully that wasn't a problem. Take care. Be good.